Good morning, everyone. Welcome to another ToloTalks session. My name is Enrique Lugo, Regional Sales Manager, and I'm going to be doing this presentation with my colleague Ryan Clementson. He's Business Development Manager. Welcome, everybody. Thank you for joining. Today, we're going to talk about pressing applications with Servo electric actuators. Basically, today, it's all about seeing the comparison between the two type of applications and technologies that are out there in the marketplace. We're gonna try to remember all the factors that are involved into pressing applications, all their main characteristics. We're gonna compare pressing systems. We're gonna talk about also load cells. Ryan is going to talk about screw basics for pressing applications, and we're going to show you a couple application examples and just finalize with some notes and the conclusion of this. So let's go ahead and start then with the general characteristics of pressing applications. So if you're familiar with this type of applications, they're normally vertical applications that the rod is pressing down. And it can be performing some type of applications such as punch dies, forming dies, bearing presses, that type of stuff, things like assembling a part into another part, the forming some metal. And normally that's done vertically. That doesn't take out the fact that you could do it also horizontally, but normally it's done vertically because you have a piece of tooling that it's normally going up and down. And this force, it's experienced normally in the extend direction, right? So you're pressing something downwards, which means that you're extending the rod. In the retract move, what you're really doing is just lifting the tooling. Some of it a lot, 200 pounds, 400 pounds, whatever. So you still need the force to do that operation, but the actual pressing force is done at the end of the stroke. The stroke lengths normally are between 12 and 18 inches. That doesn't take out the fact that there's longer, shorter strokes, but that's commonly what we see in the marketplace that it's normally used. And the force, it's applied normally in the last couple inches. For example, if you're bending metal, the metal you're bending is done only in the last 3-4 inches. If you're punching some material, it's done normally in the last quarter, last half an inch, and that's when you apply the force. As I was saying, the typical application is for punch dies, forming dies, bearing presses, etc. So we're gonna talk about the advantages and the disadvantages of hydraulic systems compared to electric systems. So let's start talking about the advantages of pressing systems with hydraulic technology. So as you know, the forces you can achieve with a hydraulic system are really high, right? So I've seen presses operating in the order of 1 million pounds of force. That's a lot of force, right? So when you're trying to do some forging for big metal pieces, you need a lot of force, and that can be achieved with hydraulics. Also, when you have one power unit, which means that it's the hydraulic reservoir, your pump, all your filters, all that stuff, and you have many cylinders using that same power unit, then the price also per cylinder can be lower than with an electric type of technology, right? Because the power unit is the main cost of this system, and the cylinder is not that expensive, so it kind of amortizes that way. Also, one of the advantages of hydraulic systems is that you can achieve the full force at any point on the stroke. The envelope required for the press itself is small. As you can see in those images, they're just simple examples there. Normally, that cylinder is operated via the power unit that was providing the actual fluid to perform the operation, but the press itself, it's pretty small. The press speeds can vary during the cycle, but the speeds you can reach are pretty slow. So there's not a way to go really fast with hydraulic systems, but it can vary during the cycle. The force also can be measured. You can measure the force in a hydraulic system, but there's not really a lot to do with that feedback of force. You can read it, but what you do with it, it's not like really great, right? So what are the disadvantages of conventional press systems such as hydraulics? So it's not really easy to maintain consistent speeds. You know, you have variations in pressure. You have variations in, you know, like the fluid going through the pipelines, etc. Temperature, all that kind of stuff can influence also the extend and retract speeds in can differ, right? So also the performance can vary with all temperature. You know, as the oil has this index called viscosity index. So if it's colder, it's thicker. If it's hotter, it's less thick. So that variation in temperature also can vary your performance that you can get out of these type of systems. The increased system complexity. Well, everybody knows how many components you need for a hydraulic system, right? You need your, so I was saying, your pump, hydraulic reservoir, filters, you need valves, you need a manifold, etc., and all the pipes to connect all the things within each other. That's a lot of stuff that you need to know what you're doing, right? And also not only know how to install all those things, but how to give proper maintenance to that. It's a higher maintenance than with an electric system, and that creates a stop in your lines, and, you know, like you have to be giving maintenance more often, etc. So besides that, you have component failures that you were not expecting. One of the most common ones is that you can contaminate the oil, and those contamination particles in the oil can also create catastrophic failures in your system, right? Besides that, the least favorite of every maintenance person, leaks, right? I've heard before this phrase in the past about hydraulic systems. It's not about if the hydraulic system is gonna leak, it's just a matter of when. Everybody knows that it's gonna leak, but it's just a matter of when. That's caused because of leaks in the hoses, in the connections between the hoses, the seals, etc. So there's a lot of complexity there that creates these disadvantages in a hydraulic system. Now let's talk about advantages in a servo mechanical press. Well, you can have more versatility in an electric press than in a hydraulic press. And why is that versatility? Well, you can control position, speed, acceleration, deceleration, and force. And with all those variables controlled, you can have more repeatability in your process, right? So that means that if you want to produce a part a certain way, you're going to do that every single time because you eliminate all the variations that we were discussing. So besides that, you have a lot of process flexibility. And one of the main things about this type of technology is that if you have, for example, changes in sizes of the products you're making, you don't have to change the whole system just because you're changing the sizes, right? So with electric or servo actuator presses, it's just a matter of a button. Those buttons come in an HMI or, you know, a program in a PLC. Then you press a button, and that way you change the size of the part you're producing. It's as easy as that, and that's why it gives you a lot of process flexibility. You can reduce the part cost because, you know, the part cost, there's a lot of costs behind producing a part, such as material, the person operating the machine, etc., etc. But if you consider something like setup time, your setup time in a hydraulic system is way bigger than with an electric system. And also, if you're changing sizes in your production line, then you don't have as many dead time, right, in between changing those production and whatever. So there's a lot of factors that reduce the part cost in actually making the part, but also you don't produce as much scrap because you can actually control what you're doing. So you produce good parts, quality parts, the throughput is higher, and also you have less downtime. Some other advantages are that you can run them in a closed loop, which means that you can get feedback directly from an encoder, which is what we normally use for getting feedback of position mainly. And also you can get feedback of force with a load cell, right? So The two of them can talk to each other and make some combinations of numbers in your PLC or your controller, and then compensate for those variances. Then you can also do a really less difficult machine build, because in this case, less components is easier, right? So you don't have to be bending any tubes for hydraulic lines. You don't have to do tuning things in. And also not only tuning things in and the time that it takes, but you have to have a person that knows how to do it. The system also has less components as hydraulics, as I was mentioning, and you have a lot more potential for faster cycle times than with a hydraulic system. Not everything is great. There's other things that servo mechanical press has things to improve. One of them is that, with a normal servo system, you typically can reach today forces up to 50 tons. So that's what we can offer right now. In the automation world we live in, 50 tons is pretty sufficient. But as I was saying, there's other operations such as mobile or forging of metals, that kind of stuff the forces are really high. So, but in our world, 50 tons is adequate, but we can improve that. Upfront cost is generally higher than the other types. So let's say that you're comparing one hydraulic cylinder to one electric cylinder. The initial cost, if you're just comparing 1 to 1, yeah, probably the electric system will be higher in cost. Obviously the operational costs are way lower, but the initial investment is higher. If you start talking about many cylinders of hydraulic cylinders with the same power unit, that's what decreases its price. When it's 1 to 1, they're not that far from each other. So a lot of customers also haven't heard of electric press operations. So it's new for some users, and that can take a little bit of resistance to change from hydraulic or pneumatic or a conventional flywheel press to electric, right? But if you realize that it's pretty easy to program, it's easy to operate, then that change is easier to put in front of some users. All right, we're going to talk now about load cells. A load cell is basically a device that provides you with two main things. It records the particulars of a press, and it provides real-time feedback to a PLC, allowing single cycle adjustments or alarms, right? So there's two types of load cells. One is the spring type, and the other one is the PSO type. The spring type are more accurate and don't require preload, but are fragile. Some people tell me, I don't want to install a load cell because I could break it, and I don't want to spend money on that if I know I'm going to break it. So it's just a matter of adjusting your system and probably selecting a load cell that is not as fragile. And a PSO type of a load cell uses a crystal under a preload to measure force. More rugged and easier to implement, and more commonly used than spring type. So the PSO is what you would normally see in a normal operation. We use this in this demo that I'm going to show you in a second here. We're using an actual load cell to measure force in real time. That's one of the things that are used a lot in operations out there, because you need a certain force to press, to punch, to form a metal. You need some type of feedback that tells you how much force you're using. And if you can do it real time, that's the best case scenario, right? So in this case, I'm going to show you this demo real quick here. So if you go bring your attention to the video feed. So basically, this is one of our RSA products. This is a motor right here. Actually, you can see it pretty well. There we go. So this that you see up here, it's one of our ACSI motors. It's a servo motor, and it's connected to this mechanical piece that is the actuator. This actuator is called an RSA, and we use this RSA in many pressing applications. Do that, it goes up to 13 1,000 pounds of force. And we have even higher than that. But this family, we go up to 13,000 pounds of force. And as you can see, it's performing a really simple operation. This is just a rubber band. It's pressing it down. And by pressing it down, the more you compress that rubber band ball, the more force you need, correct? So this load cell is providing this force feedback in real time. And that way you can tell in any point of the stroke move how much force you're developing. So that's a great tool for us. We can also, in some cases, get that feedback directly from current only, but in this case, a load cell is way more accurate, and that way you're able to, control your process better. So we're gonna go with Ryan now. He's gonna talk about the key screw technologies, and I'll go from there.
Thank you, Enrique. Good morning, everybody. Again, my name is Ryan Clementson. I'm one of the business development managers here at Tolomatic. Thank you for joining. So Enrique did a great job talking about the upside of both conventional hydraulic presses and also electromechanical presses like we manufacture components for here at Tolomatic. And so I wanted to spend just a little bit of time going through how do we size them, how does it work, how do we get them to survive a pretty aggressive service life of loading very repeatedly in a very small area of space. And so the way that we do that is going to be through the use of two different screw type technologies that are commonly available today, ball screws and planetary roller screws. And the benefits of ball screws typically is that their cost of acquisition is much, much less than planetary roller screws. So they're very effective when your forces maybe happen over a longer distance of force, or if your positioning is not nearly as critical as you might from a roller screw. And so then when you go to the roller screw, they are a little bit more expensive. And the reason is that, as you can see from the picture on the left to the right, the ball screws have a smaller area of contact and load sharing between the rolling element and the driven element. Whereas with the roller screws, that's a precision ground, very tightly controlled mating surface where you increase the load sharing surface area of the units. And because it's more of a flat on flat, it is slightly curved, but it's a higher degree of contact area. Roller screws do a nicer job when you're constantly pressing in a very small area of time repeatedly, and even when your move distances are very, very small in between those moves. You won't get spalling, point loading, premature wear and fatigue on ball screws without having to oversize them to accommodate that. So we can do higher forces with a smaller mechanical assembly in a roller screw than typically you're going to be able to with a ball screw. And so one of the other things, or where this becomes important, is in how long is it going to last? Everybody wants to know how long is my machine going to survive. And so the general commonly understood way of doing so is by using this L10 or B10 that's identified by ISO and ABMA, where it's a statistical sample size where you're going to meet or exceed this calculation in a given application under ideal conditions. And so it's a cubic function, as you can see by the formula. We're not going to go through that, but what you're seeing is the value of a roller screw in an equivalent size. And so we talk about, like Enrique mentioned with our RSA 24, this is the next size up, our RSA 32, where we've got a 2-turn per inch ball nut, a 5-turn, and then we have an RNO5, which is a 5mm lead, works out to be close to like a 4-turn. And you can see in the same size product family with different technologies of screws, your ability to provide thrust is a lot higher. About almost 2x from the 2-turn to the RNO5. And when you run this L10 cubic function using these values, you can see in an instance where you want to do about 950 pounds of force, it's almost like a 6x multiplier in life. And so if longevity is important, if size is very important, you can optimize both of those aspects by using a roller screw versus a ball screw. And so we've had tremendous success for many years using roller screws in these types of applications. And we've done a lot of testing with these numbers and with these these different products, and we've seen the benefits of roller screws in pressing applications. And here's kind of a unique example that we're seeing that even we're taking into account more so than you would with conventional math, is that in pressing applications like Enrique talked about, your force is typically going to be in one direction. And oftentimes you're going to have a rapid acceleration, and then you're going to encounter your resistance or your load, and then you'll have a high degree of force at the bottom end of your stroke. And if you were to run the L10 calculation from the prior screen where they talk about equivalent loads, that's your average, your math would actually look quite a bit different than what it will in reality. And so we've kind of come up with some guidelines whereby when your force applies within one revolution of the screw, you're going to want to take that into consideration, how you understand what your life is going to be. And we can help you with that. We don't want to overly complicate this discussion today, but we want to just at least make you aware of there's a number of ways that we can help you understand your pressing applications. We can help you understand your life, and also to paint the picture that there's a lot of understanding involved on not only picking an actuator, but determining its life, determining how it's going to last and how it's going to behave in these types of applications. And so certainly let us know. We've got our sizing software that we can use to also mimic these applications, and I'll talk more about why that's important in a minute, but we can certainly kind of assist you in answering questions and steering you down the path of what's going to make the most sense. And why I say this is all important, even outside of life, is that there's a little bit of know-how in conventionally picking a roller screw. And so roller screws act similarly to servo motors in that they're not 100% efficient, and that lack of efficiency comes out in heat. And so in our case, we generally will say a roller screw is about 80% efficient. And as it runs, if it runs very, very fast under no load, it'll create heat. If it runs very slow under load, it creates a similar amount of heat. And so you need to be monitoring this thermal rise as a function of life, as a function of lubrication and maintenance. And so that's where using a tool like our sizing software is extremely important, because we've got that built into the modeling. So as you make a rapid move with no load, a slow move with a high load, we're monitoring what that thermal rise is going to be in the component, which is going to help you determine the most appropriate solution for longevity, price, size, life, everything. And so certainly let us be a guide to going through that process with you. And so here's just an example where it's a very low force move. It's a little bit higher than what you see here, but I'm showing some calculated outputs in our sizing software, and you see that we actually do have a thermal check. And in this instance, I just did a straight out and a straight back move with no dwells. And so we're assuming that it's just reciprocating. It's continuously moving. There's no brakes. There's no relief for the heat to dissipate. And so the way that we see this is that you'd exceed our guidelines by 1%. Now, that doesn't mean it's going to fail. That doesn't mean it's not going to work, and it doesn't mean that it's not going to last. But what that means is that now you need to start taking into account, what's my maintenance schedule going to look like? How often am I going to have to grease it? If I slow it down, can I reduce my maintenance? So it's a guide of not necessarily whether or not it's going to be successful or not. It just, again, helps you understand what's going on mechanically in the device as you're running it within a simulated environment. And so we can give you a lot of this information, and we can kind of talk through what all of this means. And then we're also calculating those L10 calculations from the prior slides. So we give you a lot of information and a lot of direction in our software. And that's a free software, by the way, that's available online for anybody to use and download. And then we have applications engineers here that can answer any questions, walk you through it for the first time, or even just do one with you and help you understand how to use it. So I got a little bit ahead of myself, and like I said, the thermal limit doesn't mean that it failed, right? And so as the heat rises, all greases have a limit of effective lubrication ability. And it's not straightforward as in, kind of like what Enrique mentioned with viscosity of oil. Once you hit, let's just say 250 degrees Fahrenheit, the grease is going to quit working. Its effectiveness will actually degrade as you get higher to the rated temperature of the grease. And so that's why we kind of set this limit of where we know the grease is most effective, and you can go a little bit longer between lubrications. And so we just want to, again, make sure that we help you understand that because it doesn't pass doesn't mean it's going to fail. It means that additional considerations and a little bit of thought should go into what's going on, why is this behaving this way. Let's make sure that we're doing the planning and the diligence up front so that this becomes a successful installation. So I'm going to pass it back to Enrique, and he's going to talk about an application or two, and then I'll do another one, and we'll wrap up shortly. So Enrique, back to you.
Thank you, Ryan. Yes, so hydraulic systems, not only in terms of operational ease to program them and to run them, sometimes you can really not use them. For example, in applications such as food and beverage, pharmaceutical applications, that type of stuff, you cannot have contamination or leaks because you contaminate the product and that's it. So that's the type of applications that we really go after. And in this case, we went after this hamburger former. So this basically is that they wanted an electric actuator that was a drop-in replacement. They needed a high force, and they also needed to conserve a small footprint in terms of the machine. So our RSX unit is like the big brother of this RSA that you see here. The RSX unit is the unit that actually was designed specifically for hydraulic replacements due to the fact that it can create extreme forces. Not that you need the force during the whole cycle. You can program where you use your force, right? So in this case, hamburger, if you press too hard, then that patty is just gonna be completely like this, and then that way you're not controlling the thickness of the patty, right? So you need to control position, you need to control force. If you wanna reach a certain amount of production rate, you also need to control the velocity, acceleration and deceleration. So that was a great win for Tolomatic, and we implemented one of our RSX 96 units. And the production rate that I was mentioning, the customer wanted to produce 9,000 pounds per hour of product. The strokes varied. They didn't have just one stroke. They had 9, 10, and 13-inch stroke lengths. So with the same unit, you could modify that stroke length if you wanted. You could just choose a 15-inch total and just modify it to whatever you want to do, 9, 10, or 13 with the same unit. And that control can be done with a simple button. This servo mold plate, low maintenance. High forces normally would need more maintenance in a hydraulic unit. In this case, it's really low. And we're gonna go into that a little bit in a second here, but also you eliminate a lot of mechanical parts, right? So you don't have any filters, hoses, etc. So you just have your motor, your drive, and your actuator. No hydraulics used to operate or form products, which means no contamination. You don't need chains, sprockets, another motor. All of that can be eliminated and just have your footprint of the machine like reduced by a lot. The picture you see on the right is our RSX unit, the white paint version. This is a white epoxy version of the body of the actuator. And all the other components you see there are stainless steel, which means that they're gonna withstand corrosion. And you could also, normally in a food grade application, you will see some washing of the units, right? So stainless is also very good at withstanding corrosion, and also the white paint is. So this is our hygienic design of a high force actuator, and it's been pretty successful. Another application that I want to talk about today is another RSX unit that we used to put the ring on top of a barrel, and the barrel was used to store whiskey. All right, so these whiskey barrels, they need that ring on top to gather all the pieces of wood together and close it as tight as possible so the whiskey can actually stay inside of the barrel. So they needed a really, really particular motion profile, because you need to keep your production rate going, right? You need to make a certain amount of barrels per minute. So basically you need to get there, go really quick, and right before touching the ring that is going to be pressing down into the wood, you need to apply the pressure and the force at that last couple inches, right? But you need to go real quick and then slow down and then start pressing down that ring. So that was a really particular motion profile we designed on this unit, and that was only available with an electric technology, right? You cannot really do that with hydraulics, pneumatics, et cetera, et cetera. So that was one of the big factors there. Also, being that whiskey, people will drink it afterwards, you cannot contaminate it with hydraulic fluid. So that was one of the other pain points they were having. So challenges, they were working with our competition before. They didn't really have a lot of experience with Tolomatic. So that took a little bit of, like going back and forth, showing our technologies, etc. But at the end, I think it was a good solution there for them. And also, one of the things that this type of process has is that being wood, they cut it there, they make it to length, etc. You have a lot of wood contamination in the air. So our units are also designed with a capability of IP67 in this case, that can withstand dust in the air and spray of water. All right, so now we're gonna go with Ryan.
Thank you, Enrique. There's a bit of a common theme here, as Enrique mentioned. We're starting to see more and more applications where contamination is becoming a larger pain point as far as process, throughput, product quality, and things like that. And so here's another one that's not food related or whiskey barrel related, but in fact, battery manufacturing, which is kind of a hot button with all the EVs and battery consumption that we're using as consumers today. And so this was for lithium battery manufacturing. It was a manufacturer of machines to do so. And they needed to get rid of hydraulics because they were concerned with contamination of the finished product. And they were also challenged with getting hydraulics to perform consistently. So again, the more precise that they can assemble these batteries and get them assembled, the better the finished product is and the better it performs. And so the combination of those two was a really nice fit to try and displace their hydraulic cylinders with an electric actuator. And so, in fact, here's a picture of our RSX 096. These are rated for up to 30,000 pounds bidirectionally. We have a pressed version that is rated to 40,000 pounds for specific pressing applications. And so we were able to eliminate the risk of contamination. We're able to give them that closed loop feedback like Enrique talked about with the encoders and torque monitoring of the motors. And I think they didn't even require a load cell. In this case, they were just able to watch the motor current and get the force repeatability that they needed. So we were able to keep their controls actually quite simplistic by comparison. And then the next one that I'll talk about is one that we've been doing for a very long time, probably since about 2004. And this is in the body and white processes for auto manufacturing for resistant spot welding. And they had troubles for years with tooling costs, redundant tooling, repairs, replacements, maintenance, air consumption, force repeatability on the welds, weld consistency, and all of these things were able to be reduced and eliminated with the use of an integrated servo electric actuator that we now call Servo Weld. We've got tens of thousands of these units in the field. We've been doing it for a long, long time. And this is where we also were able to learn a lot about pressing applications. And the unique piece of what we did with these was by doing the integrated solution versus what you'd seen with our RSAs and RSXs, we were able to minimize the weight on the end of arm tooling for the robots. We were able to give them a more dynamically rigid system that gave them better control over position and gave them extremely good force repeatability. You see, we're talking plus or minus 30 pounds at upwards of 2,000, 2,200 pounds. And with our footprint, we were able to also provide them a global supplier solution that we're able to support, deliver, and service our products all over the world. And so this has been a major pain point for the auto industry for many, many years. And we're still seeing new automotive suppliers all over the world continue to migrate away from pneumatic-based press systems. Spotwell is basically a press where the force is happening within maybe an 1/8 inch of space or less, to go to an electric solution in a big, big way. So we've been very fortunate to be part of this industry and help them make that conversion over. So with that, I'll let Enrique speak for just a couple minutes on a few more notes. Thank you.
Thanks, Ryan. So we are working with clients all over the world, and as you know by now, everybody uses different types of metric or imperial systems. So some people tell you I need 100 kilonewtons of force and 10 inches of stroke, right? So combining metric and imperial system is very common. So, you know, you can Google and use conversion systems that use to start speaking on the same units. That's one of the things we normally consider when sizing a new actuator. Or sizing software is a great tool that you can use, but this one is normally used either in metric or imperial. So just in advance, try to have your units in the same type of system and go from there. Hydraulic systems are normally 20 to 50% oversized, and this is because with a servo mechanical actuator, you don't really have issues in terms of the static friction to start getting things in motion, right? So hydraulic systems have this disadvantage. So when you're trying to convert from hydraulic to electric, just keep this factor in mind, that probably the hydraulic system is oversized, and you don't want to also oversize a servo system, because really you just need the amount of force you need and not more. Hydraulic systems also are not efficient. They use a lot of energy, and that's one of the main advantages also of a servo system, which is really, really efficient, and you're not consuming as much energy. So your costs in terms of operational costs for energy are lower with a servo mechanical system. Most pressing systems will be reverse parallel and utilize a gearhead to increase torque. You know, normally you want to keep your envelope of your machine the smallest possible, and that for that reason you would use something like this, like a reverse parallel, instead of an inline motor that would go just make the whole thing longer, right? So normally what we've seen is that for pressing applications, you would see it this way in a reverse parallel configuration. And also for high forces, you need higher torques to increase the torque and be able to keep your motor in a smaller frame. You can use a gearhead between the motor and the actuator that helps you increase the torque. And also, we sell two types of actuators, the rod style and the rodless style. Rod style is like you would see here, it's just a rod that comes in and out. A rodless actuator is just a little carrier that goes back and forth. Normally, for a pressing application, you would see a rod style actuator. All right, so these are product offering for rod style actuators. On the left side, you will see our IMAs, which are the integrated motor actuators. It has a motor already inside that envelope, and that saves a lot of space, and they're great for repeatability and, you know, have the system pretty reduced in space. RSA and GSA. RSA, we talked about it. The GSA is just the guided version of this RSA. The ERD, which can be separated into two main categories. One is to replace pneumatic systems, which are economical. And then the other side of the ERDs is when you need something more hygienic. You need IP69K, stainless steel construction, and it's for applications where you're going to be power washing the unit or having chemicals in the environment, etc. So we have the ERDs for that. And then the RSX, which is, you know, forces, extreme forces for hydraulic replacement mainly, and up to 50,000 pounds of force on those ones. And then there's a lot of tools online if you want to talk about it, okay, I'll just go through it real quick. You can go to our website, and there's a lot of things you can check there: electric versus hydraulic, choosing the right type of screw, how to calculate electric actuators, etc., etc. All of that, it's available on our website and ready for you to take a look at it and go from there. You know, and you don't have to know everything about electric actuators. You can reach out to us too. In the main website, tolomatic.com, in the bottom left, you will see a button that says Contact an Engineer. Click on that, and you will be redirected to one of the applications engineers at Tolomatic that can help you with the selection of the product.